Deep space is actively hostile to human biology. If we want to live out there permanently, we have to solve two massive physical problems. The first is the total lack of gravity. Without it, the human body quickly breaks down. Astronauts lose between 1 and 1.5% of their bone mass every single month. Their muscles atrophy, and fluid shifts upward, causing severe intracranial pressure and permanent visual impairment. The second threat is radiation. Once you leave the protective bubble of Earth's magnetic field, your cells are constantly bombarded by lethal cosmic rays and high-energy solar wind. Current orbital outposts don't provide a permanent solution to these issues. The modules on the International Space Station are made of aluminum shells only a few millimeters thick, enough to hold air in, but incapable of blocking cosmic rays or simulating the gravity our bodies need. To survive indefinitely in the solar system, we need a structure that provides two things: aggressive rotation to simulate gravity, and immense physical mass to block out the radiation. One theoretical solution is the O'Neill cylinder, a rotating steel tube miles across. However, launching millions of tons of heavy metals out of Earth's deep gravity well is currently economically impossible. A more practical idea is to use materials already floating in space. The theory suggests finding a small solid asteroid, hollowing out the inside, and spinning it up to create artificial gravity. But recent reconnaissance missions exposed a flaw in that plan. The OSIRIS-REx spacecraft, which rendezvoused with near-Earth asteroids, brought back data complicating this vision. Most targets in the 100 to 500 meter size range aren't solid monoliths. The surface of the asteroid Bennu is a collection of loose boulders and debris. It is a rubble pile. This diagram illustrates what happens to a rubble pile if you try to rotate it. These rocks and dust particles are held together only by weak self-gravity. As the asteroid spins up, the outward centrifugal forces easily overpower those inward gravitational bonds. If engineers attempted to spin a rubble pile asteroid, it would instantly fracture and disintegrate, turning into an expanding cloud of space gravel. Engineers at the University of Rochester realized that this structural weakness could actually be the mechanism used to build the station. Their concept is called Habitat Bennu, and it proposes that rather than digging into a fragile asteroid, we must bag it. The plan relies on a massive, expandable containment envelope. Using a high-tensile material like carbon nanofiber, an accordion-like mesh would be wrapped entirely around a 300-meter rubble pile. The exterior mesh is fitted with solar-powered rubble cannons that ingest loose dust and shoot it into space. Ejecting this waste tangentially utilizes Newton's third law. Every thrown rock pushes the structure in the opposite direction, slowly initiating a controlled rotation. This turns the asteroid's useless dust into the fuel needed to spin it up, eliminating the requirement to haul thousands of tons of chemical propellant from Earth. Eventually, as the rotation rate increases, the artificial spin force exceeds the weak gravity holding the rocks together. The asteroid behaves exactly as it did before. It flies apart. But this time, that outward explosion of rock is immediately caught and contained by the high-tensile carbon bag. This graph tracks the expanding structure's radius. As rubble pushes outward, it stretches the mesh until it hits its maximum limit, plateauing at a 3-kilometer radius. Centrifugal compaction then takes over. The outward force presses the loose rock tightly together, forming a dense 2-meter-thick solid layer. Using rotation to drive expansion solves both requirements simultaneously. The result is a 2-meter-thick layer of compacted rock that matches the shielding of 100 meters of loose regolith, while the 3-kilometer radius generates a steady 0.3 g of Martian-level gravity. The result is a massive, hollow cylinder protected from the lethal vacuum. Inside, agricultural terraces and human habitats curve upward along the interior wall. Protected by thousands of tons of rock, colonizers could install solar lighting, grow sustainable crops, and live permanently without the physiological consequences of zero gravity. Habitat Bennu circumvents the requirement of shipping millions of tons of steel and radiation shielding from the surface of Earth. Instead, the primary structural mass is already in orbit waiting to be utilized. The materials required to build our largest space stations don't need to be launched from Earth. They are already floating next door, waiting for us to wrap them up and give them a spin.